What if everything we see in the night sky, the swirling galaxies, the drifting stars, the vast emptiness between them, is just the surface of a far deeper truth? Beneath the chaos of the cosmos lies an invisible architecture, a hidden framework of gravitational forces that sculpts the universe itself. These forces act like cosmic fingerprints, leaving behind patterns so precise they reveal a design we're only beginning to understand. Think of it as stumbling upon the blueprints of reality, etched not in ink but in the very fabric of space and time. For centuries, astronomers gazed at the heavens and saw randomness, a scattering of stars with no apparent order. But now, cutting-edge research has uncovered something astonishing. The universe isn't chaotic at all. Instead, it's guided by an intricate web of gravitational pulls, a silent symphony of forces that shapes everything from the smallest particles to the largest superclusters of galaxies. These gravitational patterns are more than just curiosities. They're clues to the universe's best-kept secrets. Dark matter, the mysterious substance that makes up most of the cosmos, leaves its mark here. The birth and death of galaxies follow rhythms written in this hidden code. Even the fate of the universe itself might be encoded in these cosmic blueprints. This isn't just science, it's a detective story on the grandest scale imaginable. Every discovery peels back another layer, revealing a cosmos far more structured, far more deliberate than we ever dreamed. And the most thrilling part, we're only at the beginning. Today, we'll follow the trail of these gravitational clues, from the brilliant minds who first noticed them to the revolutionary tools now uncovering their secrets. We'll explore how these patterns challenge our understanding of reality, how they hint at forces beyond our current grasp, and how they might even rewrite the story of the universe itself. So settle in, because by the end of this journey, you'll never look at the night sky the same way again. Einstein once described gravity not as a force but as the bending of space and time itself, a cosmic dance floor where massive objects leave their footprints. 100 years after his prediction, we finally learned to listen to those footsteps. Gravitational waves are the echoes of distant collisions, the tremors sent across space-time when black holes spiral into each other or neutron stars tear themselves apart in spectacular explosions. These waves don't just tell us about the events that created them, they carry encoded messages about the very structure of reality. Think of space-time as a vast, silent ocean. When two massive objects merge, they send ripples racing outward at the speed of light, warping the fabric of existence itself. For decades, these waves were just theory, until instruments like LIGO and Virgo turned hypothetical whispers into measurable signals. The first detection in 2015 wasn't just a scientific milestone. It was like discovering a new sense, a way to perceive the universe beyond light or sound. Suddenly, we could hear the cosmos speaking in vibrations too subtle for any telescope to see. What's truly astonishing is what these waves reveal about the universe's hidden order. When black holes collide, their gravitational waves follow precise mathematical patterns, like musical notes in a cosmic symphony. The frequencies, the decay of the signal, even the way the waves distort as they travel, each detail holds clues. Scientists now believe these patterns might expose secrets about dark matter, the nature of space-time, even the possibility of extra dimensions. It's as if the universe left breadcrumbs in the form of ripples, guiding us toward something far grander than we imagined. The more we listen, the stranger the symphony becomes. Some gravitational waves arrive distorted, as if they've passed through invisible structures we can't yet detect. Others hint at black holes of impossible sizes, defying our models of how stars live and die. With every new detection, the cosmos seems less like a chaotic accident and more like a puzzle meticulously assembled. We're not just observing the universe, we're decoding its blueprints one vibration at a time. Dark matter is the universe's greatest ghost story, an invisible presence we can't see, touch, or detect directly, yet its fingerprints are everywhere. Picture a sculptor shaping clay without ever touching it, or a puppeteer pulling strings you can't see. That's dark matter's role in the cosmos. It doesn't emit light or interact with ordinary matter in any way we've yet observed, but its gravitational grip is unmistakable. Without it, galaxies would fly apart, their stars scattering into the void like marbles dropped on a tilting table. The evidence for dark matter isn't just compelling, it's written into the very motion of the universe. When astronomers measure how fast stars orbit the centers of galaxies, they find something bizarre. The outer stars move just as fast as the inner ones, defying the laws of gravity as we know them. According to Newton and Einstein, those outer stars should be slowing down like runners tiring at the edge of a track, but they don't. Something invisible, something massive, must be holding them in place, a cosmic glue we call dark matter. Then there's the way galaxies cluster together, drawn into vast filaments and walls that stretch across billions of light years. These structures shouldn't exist without some unseen scaffolding, some hidden framework stronger than gravity alone. Computer simulations show that without dark matter, the universe would look nothing like it does today, just a sparse, formless haze. Instead, we see a cosmos intricately woven, as if stitched together by an unseen thread. But what is it? The leading theory suggests dark matter is made of particles unlike anything in our periodic table, slow-moving, cold, and nearly impossible to detect. Scientists have built detectors deep underground, shielded from cosmic rays, waiting for the faintest whisper of a collision between dark matter and ordinary atoms. So far, silence. Others propose that dark matter might not be particles at all, but a sign that our understanding of gravity is incomplete, that Einstein's equations need revising on cosmic scales. The mystery only deepens when we look at gravitational lensing, where the gravity of massive objects bends light like a magnifying glass. Some of the most striking examples show light warping around what appears to be empty space, ghostly halos of dark matter distorting the very fabric of reality. These cosmic mirages are like finding footprints in the snow with no one around to make them. Every clue points to the same conclusion. Dark matter isn't just a minor player in the universe's story. It's the architect, the unseen hand that shaped everything we see. And as we peel back the layers of this enigma, we're not just solving a cosmic puzzle, we're rewriting the rules of existence itself. If the universe has a skeleton, galactic filaments are its bones, an invisible scaffolding stretching across the void in threads so vast they make entire galaxies look like beads on a string. These filaments are the largest structures in existence, some spanning over 500 million light years, woven together by the gravitational pull of dark matter. Picture a spider's web glistening with dew, where each droplet is a galaxy clinging to these cosmic strands. But unlike a web, this structure isn't static. It's a dynamic superhighway funneling gas, energy, and even entire galaxies toward dense intersections called nodes, where galaxy clusters collide and merge in spectacular displays. For decades, astronomers puzzled over why galaxies weren't scattered randomly, but instead seemed to line up like cities connected by invisible roads. Then, gravitational lensing gave us the tools to map the unseen. When light from distant galaxies bends around these filaments, it reveals their hidden mass, tracing outlines of dark matter so massive they warp spacetime itself. The most stunning part, These filaments aren't just relics of the past, they're actively shaping the universe's future. Gas flows along them like rivers feeding galactic growth, while their gravitational tides spin galaxies into alignment, as if the cosmos itself is following an instruction manual. What's truly mind-bending is how precise this design appears. Simulations of the early universe show that tiny quantum fluctuations, random ripples in the fabric of reality after the Big Bang, somehow grew into this intricate web. It's as if the universe knew exactly where to place each thread, each intersection, to create the perfect conditions for galaxies to form. And at the heart of this design lies a paradox. The very emptiness between filaments, those vast cosmic voids, might be just as important as the threads themselves. These voids act like expansion chambers, their hollowness allowing filaments to stretch and tighten, guiding the universe's growth like an invisible hand. Now imagine zooming out far enough to see the entire cosmic web. From that perspective, the universe isn't a chaotic explosion. It's a carefully woven tapestry, with each filament a brushstroke in a masterpiece billions of years in the making. And just as highways shape human civilization, these filaments dictate where galaxies thrive, where stars ignite, and where black holes, those enigmatic engines lurking in galactic cores, might just hold the next piece of the puzzle. Black holes have long been painted as the universe's ultimate monsters, cosmic vacuum cleaners, sucking in everything that ventures too close. But what if we've misunderstood their role? Far from mere destroyers, black holes are the unseen architects of cosmic order, wielding gravity like a sculptor's chisel to shape the very galaxies they inhabit. At the heart of nearly every galaxy, including our own Milky Way, lurks a supermassive black hole, a gravitational titan millions or even billions of times heavier than our Sun. These aren't passive giants, they're dynamic engines regulating the birth and death of stars with precision. Take the way they control star formation, for example. When a black hole feeds on surrounding gas and dust, it doesn't just swallow material silently, it unleashes torrents of energy, heating up nearby clouds so intensely that they can't collapse into new stars. It's as if the black hole acts as a cosmic thermostat, turning star formation on and off like a switch. In some galaxies, this process is so extreme that entire regions become stellar deserts, frozen in time by the black hole's influence. Yet in others, the same gravitational forces compress gas into dense nurseries, sparking bursts of star birth. This delicate balance suggests black holes don't just live in galaxies, they shape them, molding their structure over billions of years. Then there's the way they orchestrate motion on a grand scale. Stars near a galactic center don't orbit randomly. They follow precise paths dictated by the black hole's gravity, like planets circling a sun. But the influence doesn't stop there. Some supermassive black holes eject jets of particles at nearly the speed of light, carving out vast bubbles in intergalactic space and even pushing entire galaxies into alignment. These jets can stretch for thousands of light years, acting like cosmic compass needles that magnetize the chaos around them. But perhaps the most tantalizing clue lies in the gravitational waves black holes produce when they collide. Each merger sends ripples through space-time, vibrations that carry encoded secrets about the nature of reality itself. Some theories propose these waves might reveal hidden dimensions, tiny, curled-up layers of space too small for us to see directly. Others suggest black holes could be bridges to entirely different universes, their intense gravity warping space-time into tunnels we've yet to comprehend. Now imagine zooming in even further to the quantum scale. Here, the rules of gravity and quantum mechanics collide in ways that challenge our understanding of physics. At a black hole's edge, particles flicker in and out of existence, their fleeting lives governed by probabilities rather than certainties. Some scientists believe these quantum fluctuations might hold the key to unifying gravity with the other fundamental forces, solving one of the greatest puzzles in modern physics. What's clear is this: black holes aren't just endpoints for matter, they're crossroads, places where gravity, quantum physics, and the very fabric of spacetime converge. And as we peer deeper into their mysteries, we're not just studying cosmic phenomena, we're decoding the universe's hidden blueprint, one gravitational whisper at a time. If gravity shapes the cosmos on the grandest scales, what happens when we zoom way into the realm of the unimaginably small? At the quantum level, the rules of the universe seem to unravel. Particles pop in and out of existence. Matter behaves as both a wave and a particle. Yet gravity, the force that sculpts galaxies and bends light, refuses to play by the same quantum rules. This isn't just a scientific inconvenience, it's a glaring rift in our understanding of reality itself. The problem starts with scale. In the quantum world, particles interact through forces carried by other particles, photons for electromagnetism, gluons for the strong nuclear force. But gravity, according to Einstein, it's not a force in the traditional sense. It's the curvature of spacetime, a geometric dance where massive objects warp the stage they move on. When physicists try to describe this curvature at the quantum scale, their equations explode into infinities. It's like trying to use a telescope to study atoms. The tools just don't fit. Enter string theory, one of the boldest attempts to bridge this divide. Imagine the universe's fundamental building blocks aren't point-like particles but tiny, vibrating strings. Each vibration pattern corresponds to a different particle. One note might be an electron, another a quark, and gravity. It emerges from a particular vibration, a cosmic bass note threading through the fabric of reality. In this framework, spacetime itself might be woven from these strings, a tapestry so fine its threads are a billion times smaller than an atom. But strings aren't the only players in this puzzle. Loop quantum gravity takes a radically different approach, proposing that spacetime is stitched together from interwoven loops. Think of a mesh so tiny it gives the universe its structure. These loops don't exist in space, they are space. When matter interacts, it twists this mesh, creating the gravity we observe. It's a vision where the smooth continuum Einstein described becomes a pixelated network at the smallest scales. The challenge is testing these ideas. Quantum gravity operates at energies so extreme they haven't existed since the first moments after the Big Bang. Yet hidden in the oldest light in the universe, the cosmic microwave background, there might be clues. This faint glow, the remnant heat of the universe's birth, carries imprints of quantum fluctuations stretched across the cosmos by inflation. Some theories predict these patterns should bear subtle scars from spacetime's quantum structure, like finding fingerprints on a primordial canvas. Then there's black holes, nature's ultimate quantum gravity laboratories. At a black hole's core, all matter is crushed into a singularity, a point where gravity and quantum mechanics collide head-on. Hawking radiation, the faint glow predicted to escape black holes, hints at a quantum layer to gravity. And when black holes merge, their gravitational waves might carry signatures of exotic physics, whispers from the edge of our understanding. What's at stake isn't just a unified theory, it's the very blueprint of existence. If we can decode how gravity operates at the quantum scale, we might finally understand why the universe looks the way it does, from the spin of electrons to the swirl of galaxies. It would be like discovering the alphabet of reality, the hidden grammar that writes everything from atoms to stars. And with each new experiment, each deeper probe into the quantum fabric, we're not just solving equations, we're reading the universe's deepest secrets, written in the language of gravity itself. The cosmic microwave background is like the oldest photograph in existence, a snapshot of the universe when it was just 380,000 years old. This faint glow, invisible to our eyes but detectable by radio telescopes, carries whispers from the dawn of time. It's not just heat left over from the Big Bang, it's a treasure map etched with imperfections that tell the story of how everything began. Look closely at this cosmic canvas, and you'll notice something extraordinary: tiny variations in temperature, patches slightly warmer or cooler than their surroundings. These aren't random blemishes, they're the fingerprints of gravitational waves, ripples in spacetime that raced across the infant universe during a period called inflation, when the cosmos expanded faster than light itself. Imagine blowing up a balloon with microscopic cracks as it inflates. Those cracks stretch into intricate patterns. The CMB's temperature fluctuations are those cracks writ large, revealing how spacetime itself was stretched and squeezed in the universe's first trillionth of a second. What's astonishing is how much these patterns reveal. The size and distribution of these hot and cold spots act like a cosmic barcode, encoding the precise strength of those primordial gravitational waves. Some theories predict these ripples should be strong, others faint, and the CMB is the ultimate arbiter, letting us test which ideas hold up. In 2014, the BICEP 2 team thought they'd found definitive proof of these waves, only to discover interstellar dust had muddled the signal. It was a reminder of how delicate this detective work is, sifting through cosmic static to find echoes from the beginning of everything. But the CMB's secrets don't stop there. Its polarization, the way its light waves align, offers another layer of clues. Some patterns swirl like whirlpools, a potential smoking gun for inflation's violent expansion. Others hint at anomalies that defy expectations, like a mysterious cold spot spanning billions of light years where the universe seems oddly empty. Could these be scars from collisions with other universes in a vast multiverse, or glitches in our understanding of physics itself? Every new map of the CMB peels back another layer of mystery. Projects like the Simons Observatory and next-generation space telescopes aim to study these patterns with unprecedented precision, searching for signals that might rewrite our origin story. And as we decode these ancient whispers, we're not just studying the past, we're uncovering the hidden rules that still govern the cosmos today, from the way galaxies cluster to the fate of spacetime itself. Now consider this: if the CMB is a baby picture of the universe, then galaxies are its adolescents, a phase where chaos and order collide. But even here, randomness isn't what it seems. Across vast distances, galaxies spin in sync, their axes mysteriously aligned like compass needles pointing toward some unseen force. These aren't chance arrangements, they're cosmic choreography, movements orchestrated by gravitational tides flowing along filaments of dark matter. It's as if the universe has a hidden rhythm, one that's been playing since the first gravitational waves rippled through the newborn cosmos. Galaxies aren't supposed to move in sync, at least not according to our standard models of the universe. Picture a crowd dispersing after a concert. Everyone moves independently, heading in different directions at their own pace. But in the cosmos, something far stranger happens. Astronomers have observed galaxies millions of light years apart rotating in eerie alignment, their axes pointing in the same direction like compass needles drawn to an invisible magnet. This isn't just a few outliers, it's a pattern stretching across billions of light years, a cosmic choreography that defies conventional explanations. The mystery deepens when we consider the forces at play. Gravity weakens with distance, and at these vast scales, it shouldn't be strong enough to coordinate such movements. Dark matter's gravitational pull can explain some clustering, but not this level of precise alignment. Some theorists suggest dark energy, the mysterious force accelerating the universe's expansion, might be tugging on these galaxies in ways we don't yet understand. Others propose even wilder ideas, that undiscovered long-range forces or remnants from the universe's earliest moments could be at work. It's as if the cosmos has a hidden rhythm, a beat we're only beginning to hear. One clue lies in the cosmic web structure. Galaxies aren't scattered randomly, they're strung along filaments of dark matter like pearls on a necklace. These filaments might act as cosmic highways, channeling galaxies into alignment through gravitational tides. Simulations show that as galaxies fall toward dense clusters, their spins can synchronize like leaves caught in a swirling current. But the observed alignments are more widespread and precise than these models predict, hinting that something fundamental is missing from our equations. Then there's the role of primordial magnetic fields, threads of magnetism woven into the universe's fabric since its infancy. These fields, if strong enough, could have guided galaxy formation, imprinting alignments that persist today. Or perhaps the answer lies in quantum fluctuations during inflation, stretched to cosmic scales and frozen into the distribution of matter. Whatever the cause, these alignments aren't just curiosities, they're potential windows into physics beyond our current theories. What makes this discovery so thrilling is its sheer improbability. Imagine tossing a handful of coins into the air and watching them all land facing the same direction. The odds are astronomically low unless some unseen force is guiding them. That's the puzzle astronomers face. Either we're witnessing a cosmic coincidence of unimaginable scale, or the universe is whispering secrets about forces we've yet to name. And as telescopes map more of the sky in unprecedented detail, each new observation brings us closer to deciphering this hidden chapter in the universe's blueprint. Now consider what happens when light itself bends to gravity's will. Just as these galactic alignments reveal hidden forces, gravitational lensing exposes mass we can't see, turning the cosmos into a funhouse mirror where light reveals the invisible. Gravitational lensing is the universe's ultimate sleight of hand, a cosmic illusion where light bends around massive objects, warping our view of space like a funhouse mirror. Imagine holding a magnifying glass over a newspaper and watching the letters stretch and twist. Now picture that magnifying glass as an entire galaxy cluster, its gravity so immense it distorts the light from objects billions of light years behind it. What reaches our telescopes isn't just a single image of a distant galaxy, it's often multiple, smeared or stretched into surreal arcs and rings like a reflection in a broken mirror. This phenomenon isn't just a curiosity, it's one of astronomy's most powerful tools. When light from a distant quasar bends around a foreground galaxy, it can split into four identical images, a perfect cross known as an Einstein cross. These mirages aren't just pretty, they're precise. By measuring how the light bends, scientists can weigh the lensing galaxy, including its invisible dark matter halo. It's like using a shadow to measure the shape of something you can't see. In some cases, lensing even magnifies distant galaxies that would otherwise be too faint to detect, acting as nature's telescope to reveal the universe's earliest structures. But the real magic happens when lensing exposes the invisible scaffolding of dark matter. Some of the most striking examples show light bending around what appears to be empty space, ghostly halos of dark matter warping spacetime itself. The Bullet Cluster, for instance, gave us the first direct proof of dark matter's existence. When two galaxy clusters collided, their visible gas slowed and heated up, but their dark matter, detectable only through its gravitational lensing effect, kept right on going, leaving a trail of bent starlight in its wake. It was as if the universe handed us an X-ray, revealing the skeleton beneath the skin. The distortions aren't always so dramatic. Weak lensing, a subtler effect, causes thousands of distant galaxies to appear slightly stretched, like a field of stars gently tugged by invisible strings. By mapping these tiny distortions across vast swaths of sky, astronomers have reconstructed the cosmic web in 3 dimensions, tracing the filaments of dark matter that connect galaxies across the void. It's a bit like listening to the hum of a distant engine to diagnose a machine you can't open. Yet for all its power, gravitational lensing has its quirks. Sometimes the same distant object appears multiple times in the same image, a cosmic echo created by light taking different paths around the lens. Other times, the lensing galaxy's uneven mass distribution twists the background object into a perfect ring, an Einstein ring, a halo of light that looks too perfect to be natural. These anomalies aren't just beautiful, they're clues. The exact shape of the distortion reveals the distribution of mass in the lens, down to the clumps and voids of dark matter we'd never see otherwise. Now shift your gaze to the opposite end of the cosmic spectrum, the vast, empty regions between galaxies, where lensing reveals another layer of the universe's design. These cosmic voids aren't just blank spaces, they're dynamic chambers where gravity's absence shapes the fate of everything around them. Cosmic voids are the universe's silent architects, vast, empty regions stretching hundreds of millions of light years, where galaxies are almost entirely absent. These aren't just blank spots on the cosmic map, they're dynamic forces shaping the fate of everything around them. Picture a balloon inflating unevenly, with some regions stretching faster than others. That's how voids behave, their emptiness creating a gravitational push that alters the motion of galaxies and even the flow of time itself. The sheer scale of these voids defies intuition. The Boötes void, one of the largest known, spans 330 million light-years, a cavern so enormous you could fit thousands of Milky Ways inside with room to spare. Yet it contains only a handful of galaxies, scattered like lost ships in an ocean of nothingness. What's fascinating isn't just their size, but their influence. Voids act like cosmic repellers, their lack of mass creating a kind of anti-gravity effect. As galaxies near the edges of voids, they're pushed outward, accelerated by the void's expanding boundaries. This motion offers a critical test for dark energy, the mysterious force driving the universe's accelerating expansion. By studying how galaxies flee voids, scientists can measure dark energy's strength with unprecedented precision. But voids challenge more than just our understanding of dark energy. They reveal quirks in the universe's structure. Some voids are too large to fit comfortably in our models of cosmic evolution. Their existence suggests that either the universe's initial conditions were far stranger than we thought, or that unknown forces sculpted these hollows in ways we're only beginning to grasp. Simulations of the early universe struggle to reproduce the sheer scale of the largest voids, hinting that our theories might be missing a crucial ingredient. Then there's the way voids warp time. According to Einstein, gravity doesn't just bend space, it slows time. In regions of intense gravity, like near black holes, clocks tick measurably slower. But voids flip this effect. With so little mass, time inside a void actually moves faster compared to the dense galaxy clusters outside. It's a subtle difference, but over cosmic distances, this time warp can distort our observations, stretching the light from distant supernova in ways that mimic the effects of dark energy. Untangling these illusions is like solving a puzzle where the pieces keep changing shape. What's truly remarkable is how these empty regions connect to the universe's grand design. Voids and filaments form a cosmic feedback loop. The emptiness of voids pulls matter into filaments. while the filament's gravity drains more matter from the voids, amplifying the contrast over billions of years. This dance between presence and absence isn't just a curiosity, it's the engine driving the universe's evolution. Without voids, galaxies would lack the tidal forces that spin them into disks or hurl them into collisions. Even the universe's expansion would unfold differently, with voids acting as accelerators, their emptiness pushing the cosmos apart faster than gravity can pull it back. Now imagine standing at the center of one of these voids, surrounded by darkness so complete it feels like the edge of existence. Yet even here, in the deepest emptiness, gravity's fingerprints remain subtle, pervasive, and utterly inescapable. And as we turn our gaze from these hollows to the fabric of spacetime itself, we'll see how gravity doesn't just shape space, it bends time, weaving the two into a single, inseparable tapestry. Einstein's revelation that gravity bends time as well as space wasn't just poetic, it rewrote our understanding of reality. Picture two clocks, one placed on Earth's surface, the other aboard a satellite high above. Though identical, the satellite's clock ticks slightly faster, racing ahead by microseconds each day. This isn't a mechanical flaw, it's time dilation, the direct result of Earth's gravity weakening with distance. GPS satellites must account for this effect, adjusting their timing signals to keep navigation systems accurate. Without these corrections, your phone's map would drift off course by nearly 7 miles per day, turning a drive to the grocery store into a cosmic misadventure. But the extremes of time dilation reveal even stranger truths. Near a black hole's event horizon, where gravity twists spacetime into a funnel, time slows to a crawl. An astronaut falling toward the singularity would appear frozen to distant observers, their final moments stretched across millennia. Meanwhile, from the astronaut's perspective, the outside universe would flash forward in a blur, stars aging and dying in seconds. This isn't science fiction, it's the universe's hidden mechanics laid bare. Gravity doesn't merely pull objects, it orchestrates time itself, conducting a symphony where every massive object alters the tempo. The implications ripple beyond black holes. Time dilation suggests that the universe might be threaded with invisible pathways where gravity warps time into bridges. Some theories propose that under extreme conditions like those inside a spinning black hole, time could loop back on itself, creating closed time-like curves. These aren't time machines in the Hollywood sense, but natural wrinkles in spacetime where the past and future might briefly touch. Wormholes, hypothetical tunnels through spacetime, could exploit this effect, with their entrances aging at different rates due to gravitational time shifts. Even more tantalizing is the idea that time dilation could link parallel universes. If our cosmos is one bubble in a vast multiverse, regions where gravity crunches spacetime tightly enough might thin the barriers between realities. Imagine two universes pressed together like pages in a book, their gravitational fields bleeding through. Time would flow differently in each, creating zones where the laws of physics subtly shift, cosmic seams where the fabric of existence frays. The most mind-bending part, we might already have evidence. Certain anomalies in the cosmic microwave background, those faint echoes of the Big Bang, show patterns that some physicists argue could be bruises from collisions with other universes. If true, gravity's grip on time isn't just a local phenomenon, it's the stitchwork holding the multiverse together. And as we probe deeper into these mysteries, we're not just studying time, we're unraveling the threads of existence itself. Gravity is the weakest of nature's fundamental forces, so feeble that a tiny magnet can lift a paperclip against Earth's entire gravitational pull. This oddity has puzzled scientists for decades. Why is gravity, the force that shapes galaxies and bends light, so disproportionately weak compared to electromagnetism or the nuclear forces? One radical answer comes from theories of the multiverse. Imagine gravity isn't confined to our universe at all, it's spilling into other dimensions. Its strength diluted as it bleeds across cosmic membranes we can't perceive. This idea, born from string theory and brain cosmology, suggests that what we call gravity might just be the faint echo of a force echoing through a far vaster reality. In brain cosmology, our universe could be a three-dimensional brain floating in a higher dimensional space, like a sheet of paper suspended in a vast, unseen room. Other brains' parallel universes might hover nearby, separated by distances smaller than an atom. Gravity, unlike other forces, wouldn't be tethered to our brain. It could seep into the bulk, the space between worlds. This leakage would explain why gravity feels so weak to us. Much of its influence is drifting elsewhere, tugging on realities we'll never see. The gravitational patterns we observe, the clustering of galaxies, the bending of light, might not just reflect the mass in our universe, but the hidden contours of neighboring brains pressing against our own. The implications are staggering. If gravity bridges universes, then collisions between brains could leave scars in the cosmic microwave background, faint temperature variations that hint at encounters with other realities. Some researchers even speculate that dark matter, the invisible glue holding galaxies together, could be ordinary matter from a nearby brain, its gravity reaching us while its light remains trapped. It's as if we're living in an apartment building, hearing the footsteps of neighbors through the walls but never seeing their faces. Ancient cultures, unaware of brains or quantum physics, sensed this interconnectedness too. They mapped the heavens not as random points of light, but as stories woven tapestries where gods, heroes, and celestial creatures moved in patterns reflecting earthly and divine order. The Maya tracked Venus with precision, believing its cycles mirrored the rhythms of life and death. Hindu cosmology described endless universes floating like bubbles in an infinite ocean, each breathing in and out of existence. These weren't just myths, they were attempts to read the cosmos's hidden blueprint, to find symmetry between the seen and unseen. Today, we chase the same truths with telescopes and equations. The difference is we're beginning to test these ideas. If gravity truly leaks between worlds, future experiments might catch its traces, subtle anomalies in particle collisions, whispers in gravitational wave data, or ripples in the fabric of spacetime itself. Whether through ancient star charts or quantum detectors, humanity's quest remains the same: to uncover the design written not just in the stars, but in the spaces between them. Ancient civilizations gazed at the night sky and saw more than random stars. They detected rhythms, cycles, and hidden symmetries that modern science is only now beginning to decode. The Maya didn't just track Venus for ceremony. Their astronomical tables predicted its movements with precision rivaling today's calculations, all without telescopes or Newton's laws. Babylonians mapped planetary orbits using clay tablets, their math revealing patterns that wouldn't be formally explained for millennia. These weren't mere superstitions. They were early attempts to read the universe's gravitational handwriting, long before we had the language to describe it. Take the Maya's long count calendar, an intricate system spanning over 5,000 years. At its heart lay the idea of cyclical time, where celestial events repeated in grand intervals, a concept eerily reminiscent of orbital resonances, where gravitational interactions create repeating patterns in planetary motions. Or consider Hindu cosmology, which described time as a wheel turning through ages of creation and destruction, mirroring modern theories of cosmic inflation and gravitational collapse. These cultures didn't know about dark matter or spacetime curvature, yet their models often aligned with the universe's underlying architecture. the Dogon people of Mali present one of the most puzzling cases. Their oral traditions described Sirius as a binary star system centuries before telescopes confirmed it, even detailing the orbital period of its invisible companion. While debates rage over how they acquired this knowledge, the parallel is striking. Their cosmology intuited gravitational bonds we now know govern binary stars. Similarly, Polynesian navigators crossed thousands of miles of open ocean by reading subtle gravitational clues, the way ocean swells bent around islands, a technique that echoes how astronomers today map dark matter by observing bent starlight. What's remarkable isn't just the accuracy of these ancient systems, but their shared emphasis on connectivity. Norse mythology imagined the cosmos as Yggdrasil, a great tree whose roots and branches linked realms together, an uncanny metaphor for the cosmic web's filaments connecting galaxies. Aboriginal sky stories described the Milky Way as a river flowing between worlds, much like dark matter's invisible currents shaping galactic motion. These weren't isolated myths, they were cultural expressions of a universal truth that the heavens operate as an interconnected system, bound by unseen forces. Modern probes like the Euclid Space Telescope and the Dark Energy Survey are now mapping these ancient intuitions with quantum precision. As we chart the universe's large-scale structure, we're uncovering gravitational patterns that resonate with those old cosmologies, filaments like Yggdrasil's roots, voids as expansive as the Aboriginal Dreamtime, and cycles as precise as the Maya's calendars. The difference is, we're beginning to understand the physics behind the poetry. Yet in that gap between myth and measurement lies a tantalizing question. Did these civilizations glimpse fragments of cosmic design through observation alone, or was there something deeper guiding their vision, a human sensitivity to the universe's hidden rhythms, written in gravity's silent language? As we turn from these ancient skywatchers to cutting-edge telescopes, the thread remains unbroken. The same gravitational forces they sensed indirectly now ripple through our detectors as measurable waves. The same celestial order they tracked with stone circles, now rendered in supercomputer simulations. Perhaps the greatest lesson isn't just how far we've come, but how persistently humanity has sought to read the cosmos's blueprints, whether carved in stone, written in starlight, or etched in the fabric of spacetime itself. Space telescopes have become our eyes into the invisible tools so advanced they don't just capture light, but decode the universe's hidden architecture. Take the James Webb Space Telescope, perched 1 million miles from Earth. Its infrared vision pierces through cosmic dust, revealing galaxies so ancient their light has traveled nearly the entire history of the universe to reach us. But Webb isn't just showing us distant objects, it's exposing how gravity has woven them into the cosmic web. By measuring the subtle distortions in these primordial galaxies' shapes, scientists can trace the gravitational fingerprints of dark matter, mapping its distribution across billions of light years. Then there's Euclid, the European Space Agency's dark universe detective. Unlike traditional telescopes that focus on individual objects, Euclid casts a wide net, surveying over a third of the sky with razor-sharp precision. Its mission, to create the most detailed 3D map of the universe ever made, charting the positions of 2 billion galaxies and the dark matter scaffolding that connects them. Euclid's secret weapon is gravitational lensing, measuring how light from distant galaxies bends as it passes through invisible dark matter halos. The result is like an X-ray of the cosmos, revealing the skeleton beneath the flesh of visible stars and gas. But these instruments don't work alone. Ground-based observatories like the Vera Rubin Observatory in Chile complement space telescopes with wider field views, capturing fleeting cosmic events that help calibrate our models of galactic motion. Together, they form a network of cosmic cartographers, each tool adding another layer to the map. The Rubin Observatory's legacy survey of space and time will image the entire southern sky every few nights for a decade, creating a time-lapse of the universe's evolution. Imagine watching a city grow from a village to a metropolis, except this city spans billions of years, and its blueprints are written in gravity's hand. What's emerging from these observations is a universe far more structured than we ever imagined. Galaxies don't just cluster randomly, they align along filaments with eerie precision, as if drawn by an unseen artist. Some filaments stretch over 500 million light-years, their gravitational pull funneling galaxies into dense nodes where they collide and merge. These aren't static structures, they pulse with motion, galaxies streaming along dark matter highways like commuters in a cosmic rush hour. Now, to make sense of this deluge of data, scientists turn to supercomputers, crafting digital universes that evolve over billions of simulated years. These aren't mere animations, they're laboratories where physicists test theories of dark matter, dark energy, and the very laws governing cosmic growth. By tweaking variables, adjusting dark matter's properties, or the strength of dark energy, researchers watch how virtual galaxies form, comparing the results to real telescope data. It's like running 1,000 alternate histories of the universe, searching for the version that matches reality. And when simulations and observations align, we catch another glimpse of the universe's hidden design, a blueprint written not in ink, but in gravity's silent, irresistible pull. Cosmic simulations are like time machines for the universe, digital laboratories where scientists recreate 13.8 billion years of cosmic history in a matter of days. Inside these virtual realms, supercomputers crunch equations with such precision that they can track the birth of galaxies, the dance of dark matter, and even the subtle tug of gravitational waves across unfathomable distances. The process begins with a simple recipe. Take the known laws of physics, sprinkle in some dark matter and dark energy, then press play and watch as the simulation unfolds from the Big Bang to the present day. What emerges isn't just a pretty animation, it's a mirror of reality, one that often matches telescope observations with uncanny accuracy. These simulations reveal something profound, that the universe's most intricate structures, from galaxy clusters to cosmic voids, emerge naturally from gravity's relentless pull. Run enough variations and patterns start to appear. For instance, when researchers tweak the properties of dark matter, making it warmer, colder, or more interactive, the resulting virtual universes look radically different. Some produce too many galaxies, others too few. But when the settings align just right, the simulation spits out a cosmos that looks eerily like our own, complete with the same filamentary webs and galactic alignments we see through telescopes. It's as if we've stumbled upon the universe's default settings, the hidden parameters that govern everything from the smallest dwarf galaxy to the largest supercluster. One of the most startling discoveries from these simulations is how small initial differences snowball into cosmic-scale diversity. Tiny quantum fluctuations in the early universe, random blips smaller than an atom, get stretched by inflation into vast density variations. Gravity amplifies these differences over billions of years, sculpting them into the galaxies and voids we see today. The simulations show this process in exquisite detail, tracing how dark matter's invisible scaffolding guides ordinary matter into the luminous structures we recognize as stars and galaxies. It's a cosmic domino effect, where the faintest whispers of gravity in the universe's infancy echo across eternity. Yet even the most advanced simulations have their limits. Some galactic features, like the precise number of satellite galaxies orbiting the Milky Way or the internal structure of dark matter halos, still don't match observations perfectly. These discrepancies aren't failures, they're clues, pointing to gaps in our understanding of dark matter's nature or gravity's behavior on cosmic scales. Some theorists speculate that gravity itself might not be a fundamental force at all, but an emergent phenomenon, a side effect of deeper, more primal laws we've yet to uncover. This idea that gravity could be an illusion sounds like science fiction, but it's rooted in serious physics. Just as temperature emerges from the chaotic motion of molecules, gravity might arise from the entanglement of quantum information across spacetime. In this view, the force that binds planets and bends light isn't an independent entity but a collective behavior, like the way individual ants create the illusion of a single, intelligent colony. Simulations testing these theories are pushing supercomputers to their limits, probing whether gravity's familiar pull could be the cosmic equivalent of a mirage, a shadow of something far stranger lurking beneath the surface of reality. The implications are staggering. If gravity is emergent, then black holes, dark matter, even the expansion of the universe might all be symptoms of a deeper code waiting to be cracked. Simulations are our best tool for exploring this possibility, letting us rewind and fast-forward hypothetical universes where gravity operates differently. Already, some models suggest that emergent gravity could explain galactic rotation curves without invoking dark matter at all, a radical idea that, if proven, would rewrite textbooks overnight. What's clear is this: every time we run these cosmic simulations, we're not just testing theories, we're peering into the universe's hidden operating system, line by line. And with each iteration, we move closer to answering the ultimate question: is gravity the architect of the cosmos, or just one actor in a much grander play? What if gravity isn't a force at all, but an illusion, a side effect of something far more fundamental? This radical idea, known as emergent gravity, flips centuries of physics on its head. Picture a bustling city seen from above. Cars move along streets, people crowd sidewalks, traffic lights cycle, all seemingly governed by their own rules. But zoom out further, and you realize these patterns emerge from something deeper: the city's layout, its laws, even the unspoken rhythms of human behavior. In the same way, emergent gravity suggests that what we perceive as a fundamental force might actually be the collective behavior of something more primal, information itself. At the heart of this theory lies a startling claim: gravity doesn't originate from objects pulling on each other, but from the way quantum information intertwines at the edges of space-time. Eric Verland, a theoretical physicist, compares it to the way temperature arises from the motion of molecules. You can't point to a single molecule and say, "This one holds the heat." Temperature is a collective property. Similarly, Verland argues gravity isn't a standalone force but a statistical effect, a byproduct of how entropy, the universe's tendency toward disorder, reshapes the fabric of reality. The implications are staggering. If gravity emerges from information at the universe's boundaries, it could explain cosmic mysteries that have baffled scientists for decades. Take dark matter, for example. Instead of invoking invisible particles, emergent gravity suggests that what we call dark matter might just be ordinary matter responding to the way information is structured at cosmic scales. In this view, galaxies rotate the way they do not because of some unseen substance, but because spacetime itself stores and processes information differently than Einstein's equations predict. Support for this idea comes from an unlikely place: black holes. When matter falls into a black hole, it doesn't just vanish. Its information gets smeared across the event horizon, a phenomenon known as the holographic principle. This principle suggests that all the information inside a black hole can be encoded on its surface, like a cosmic DVD where three-dimensional reality is projected from a two-dimensional boundary. Emergent gravity extends this logic to the entire universe, proposing that what we experience as gravity is just a holographic projection of deeper quantum processes. Critics argue that emergent gravity hasn't yet passed all the tests traditional gravity theories have, like precisely predicting the motion of stars in distant galaxies. But proponents counter that the theory is still in its infancy, like general relativity was a century ago. What's undeniable is how this perspective reframes our place in the cosmos. If gravity is emergent, then the universe isn't just governed by forces, it's a computational system, processing information on scales we're only beginning to fathom. Now consider how this ties into the universe's earliest moments. Cosmic inflation, the explosive expansion that shaped the infant cosmos, left behind gravitational imprints, ripples in spacetime that eventually grew into galaxies and voids. If gravity is emergent, those imprints might carry clues about the deeper processes that birthed them. It's as if the universe left a trail of breadcrumbs in gravity's code, waiting for us to decipher their true meaning. The theory of cosmic inflation paints a picture of the universe's birth so dramatic it defies intuition. A trillionth of a second after the Big Bang, space itself erupted in a growth spurt so violent it outpaced the speed of light. This wasn't expansion as we know it today, with galaxies drifting apart like dots on an inflating balloon. This was space-time stretching at a rate so extreme it ironed out every wrinkle, leaving the cosmos suspiciously smooth in its aftermath. Yet hidden in that smoothness were quantum ripples, tiny fluctuations that gravity would later amplify into galaxies, stars, and everything we see around us. These primordial wrinkles didn't just shape matter, they left their mark on spacetime itself. As inflation stretched the universe, it generated gravitational waves, ripples in the fabric of reality that have been traveling undisturbed for nearly 14 billion years. Unlike the gravitational waves we detect from black hole collisions, these are far older and far fainter, a whisper from the universe's first moments. Finding them would be like uncovering the fingerprints of creation, direct proof that inflation happened, and a window into energies so high they make particle colliders look like toys. The hunt for these cosmic birthmarks has led scientists to some of the most remote places on Earth. At the South Pole, telescopes like BICEP scan the cosmic microwave background, the afterglow of the Big Bang, searching for telltale swirls in its polarization patterns. These spirals, known as B-mode polarization, would be the smoking gun of inflation, created when primordial gravitational waves stretched spacetime in specific directions. Initial excitement in 2014 gave way to caution when interstellar dust muddied the signal, but next-generation experiments like the Simons Observatory are now closing in with unprecedented sensitivity. What makes these waves so revolutionary isn't just their age, it's what they reveal about gravity's role in the universe's first moments. Inflation's gravitational waves would carry clues about the energy scale at which it occurred, hinting at physics beyond the standard model. Some theories suggest inflation was driven by a field so powerful it temporarily unified all fundamental forces, including gravity, into a single superforce. If so, these waves might encode secrets about quantum gravity itself, a regime where spacetime ceases to be smooth and becomes a frothing sea of uncertainty. Now, shift focus from the universe's birth to its most violent present-day events: black hole collisions. When two black holes spiral toward each other, they warp spacetime so intensely that the resulting gravitational waves can be detected across billions of light years. These mergers aren't just cosmic spectacles, they're extreme laboratories for testing gravity's limits. Einstein's theory predicts exactly how the waves should look, their frequency, amplitude, and decay, but what if they deviate? Some observations already hint at anomalies, like black holes of impossible sizes or merger rates higher than expected. Could these be signs of new physics, or even echoes of inflation's primordial conditions echoing through cosmic history? The connection runs deeper than coincidence. Just as inflation's waves imprinted patterns on the early universe, black hole mergers sculpt spacetime in ways that reveal its underlying structure. Some theorists propose that certain gravitational wave signals might carry traces of extra dimensions, predicted by string theory but hidden from our everyday perception. Others speculate that the way waves disperse could expose subtle flaws in general relativity, pointing toward an emergent theory of gravity. Every collision is a stress test for Einstein's equations, probing whether they hold true under the most extreme conditions the universe can muster. What's astonishing is how these two frontiers, inflation's whispers and black hole crashes, bookend our understanding of cosmic evolution. One captures the universe's first breath, the other its most violent exhales. Yet both speak the same language, vibrations in spacetime carrying messages about gravity's true nature. Whether we're listening for the faintest hum from the dawn of time or the thunderclap of colliding black holes, the goal remains the same: to decode the hidden rules written in gravity's hand, from the smallest quantum flicker to the grandest cosmic design. Black hole mergers are the universe's ultimate stress tests, cosmic collisions so violent they warp spacetime itself, bending the rules of physics in ways we're only beginning to understand. When two black holes spiral toward each other, their immense gravity sends shockwaves rippling across the cosmos at the speed of light. These gravitational waves carry more than just the story of a distant crash. They're encoded with secrets about gravity's true nature, especially in conditions so extreme they defy Earth-bound experiments. Einstein's theory of general relativity predicts exactly how these waves should look, from their rising frequency as the black holes approach to the abrupt silence once they merge. But what happens when the universe doesn't follow the script? Some mergers have already thrown curveballs. Take GW 1924, a collision detected in 2019 where the resulting black hole spun at nearly the maximum speed relativity allows, so fast it flirted with the theoretical limit. Then there's GW 1905-21, where one of the merging black holes fell into a puzzling mass gap, too heavy to form from a collapsing star yet too light to fit typical supermassive models. These outliers aren't just anomalies, they're potential clues to phenomena Einstein never imagined, like primordial black holes left over from the Big Bang or even exotic objects beyond our current physics, wormholes, gravistars, or other cosmic oddities lurking in the dark. The real magic happens in the details. As gravitational wave detectors grow more sensitive, they're picking up subtle distortions in these signals, echoes that might reveal whether black holes have surfaces or firewalls near their event horizons, or if spacetime behaves differently in these extreme environments. Some theories suggest that if extra dimensions exist, they could subtly alter how gravitational waves propagate, leaving faint fingerprints in the data. Others propose that mergers might temporarily create bridges between distant points in spacetime, fleeting wormholes that imprint their signature on the waves before snapping shut. What makes these events such powerful laboratories isn't just their violence, it's their purity. Unlike neutron star collisions, which flood telescopes with light across the spectrum, black hole mergers are dark, leaving gravity as their only messenger. This lets scientists isolate gravity's behavior with unprecedented precision, free from the noise of gas, magnetic fields, or radiation. Each new detection sharpens our understanding, pushing general relativity to its limits and probing whether it breaks down under conditions Einstein could never have tested. Now shift your gaze from these cataclysmic crashes to the serene spin of galaxies, a puzzle that, at first glance, seems unrelated. Yet just as black hole mergers test gravity's extremes, the way galaxies rotate reveals its hidden flaws. Stars on the outer edges of spiral galaxies move far faster than predicted, as if gripped by some unseen force. This discrepancy, first noted by Vera Rubin in the 1970s, became the cornerstone for dark matter's existence. But what if the answer isn't invisible matter at all? Alternative theories like modified Newtonian dynamics or emergent gravity suggest that our equations might simply be incomplete, that gravity behaves differently on cosmic scales than in our solar system. The connection between black hole mergers and galaxy rotation might seem tenuous, but both are threads in the same tapestry. One tests gravity where it's strongest, the other where it's weakest. Together, they're forcing us to ask whether Einstein's theory, for all its brilliance, is just one piece of a much larger puzzle, one where dark matter, extra dimensions, or even deeper layers of reality might be hiding in plain sight. Galaxies spin in ways that defy simple explanation, like a carousel where the outer horses whip around just as fast as the inner ones. Physics says this shouldn't happen. When Vera Rubin first measured the rotation speeds of stars in distant galaxies, she found something startling. Stars far from the galactic center were moving far too quickly. According to Newton's laws, these outer stars should slow down, like planets farther from the sun orbit more sluggishly, yet they don't, the only way to explain their speed. Something invisible, something massive, must be tugging on them, adding extra gravitational oomph. This cosmic discrepancy became the cornerstone of the dark matter hypothesis, the idea that most of the universe's matter doesn't interact with light at all, yet its gravity shapes everything we see. But dark matter isn't the only possible answer. Some physicists propose a radical alternative. Maybe our understanding of gravity itself is incomplete. Modified Newtonian dynamics, or MUND, suggests that gravity behaves differently on the vast scales of galaxies than it does in our solar system. Instead of invoking invisible particles, MUND tweaks the equations, making gravity slightly stronger where accelerations are incredibly faint, like the outer edges of galaxies. In this view, the stars aren't speeding because of hidden mass, but because gravity's rules change in the cosmic hinterlands. It's as if the universe has a hidden set of instructions that only kick in when forces become vanishingly weak. The debate between dark matter and MUND isn't just academic, it cuts to the heart of how we understand the cosmos. Dark matter's supporters point to bullet-proof evidence like the bullet cluster, where gravitational lensing reveals massive halos of unseen matter separated from visible gas. Yet MUND has its own victories, accurately predicting the rotation curves of some galaxies without needing dark matter's fudge factor. The twist: neither theory explains everything perfectly. Dark matter struggles with certain small galaxies, while MUND falters when tested against the precise motions of galaxy clusters. It's as if the universe is taunting us with pieces from two different puzzles, refusing to let them fit neatly together. Now imagine zooming in even further past galaxies, past stars, down to the very fabric of spacetime itself. At the quantum level, empty space isn't empty at all. It's a seething foam of virtual particles popping in and out of existence, a turbulent sea that might subtly alter how gravity operates. Some theorists suggest this quantum foam could bend spacetime in ways that mimic dark matter's effects, or tweak gravity's strength over vast distances. If true, the galaxy rotation problem might not be about missing matter or flawed equations, but about the universe's fundamental graininess, a texture too fine for our current tools to resolve. This isn't just about solving a single mystery, it's about rewriting the cosmic rulebook. Whether the answer lies in invisible particles, revised gravity, or quantum spacetime, each possibility leads us closer to the universe's hidden blueprints. And as telescopes peer deeper and detectors grow more sensitive, we're not just searching for dark matter or testing Mundu, we're uncovering the invisible hand that sculpts the cosmos, one spinning galaxy at a time. At the smallest scales imaginable, where space and time dissolve into uncertainty, the universe might resemble a bubbling cauldron of chaos, a seething, turbulent froth physicists call quantum foam. Picture an ocean's surface during a storm, with waves crashing and foam churning unpredictably. Now shrink that down to a billionth of the size of an atom, and you're close to the frenzy theorized to exist at spacetime's foundation. This isn't just poetic imagery, it's a radical reimagining of reality's building blocks, where the smooth, curved spacetime Einstein described fractures into a probabilistic dance of fleeting wormholes, virtual particles, and flickering geometries. Why does this matter for gravity? Because this foam could be the missing link in one of physics' greatest puzzles. Why gravity stubbornly resists unification with quantum mechanics. While the other fundamental force is electromagnetism, the strong and weak nuclear forces play by quantum rules, gravity marches to its own drum. Quantum foam offers a tantalizing clue. If spacetime itself is unstable at these microscopic scales, then gravity's apparent weakness might not be a fundamental property but an illusion, a side effect of the foam's chaotic churn diluting its influence. Imagine trying to measure the depth of a turbulent river with a ruler that keeps dissolving. That's the challenge of quantifying gravity in a frothy spacetime. The implications ripple outward. Some models suggest that as gravitational waves travel through this quantum foam, their paths might subtly distort, like light shimmering through heat haze. Advanced detectors like LIGO and future space-based observatories could one day catch these distortions, revealing spacetime's granular texture. Even more intriguingly, certain theories propose that the foam's fluctuations might leave faint scars on the cosmic microwave background, ancient imprints from when the universe was so small that quantum gravity dominated. Finding these scars would be like uncovering fossils from the universe's first moments, proof that spacetime wasn't always the smooth continuum we experience today. Now zoom out from this microscopic chaos to the cosmic scale. The same quantum fluctuations that froth spacetime at the tiniest levels might have been stretched to astronomical sizes during inflation, seeding the gravitational patterns that later sculpted galaxies and dark matter halos. It's a breathtaking connection. The universe's largest structures could owe their existence to the smallest, most violent processes imaginable. This interplay between the infinitesimal and the infinite hints at a deeper truth, that gravity's patterns, from spiraling galaxies to colliding black holes, might all be threads woven from the same quantum fabric. Yet the foam's turbulence raises existential questions about the universe's fate. If spacetime is fundamentally unstable, could regions of it someday boil over, unraveling the fabric of reality itself? Or might the foam's energy fuel cosmic expansion in ways we've yet to comprehend? These aren't just thought experiments, they're clues to whether the cosmos will end in heat death, a big rip, or something stranger still. Every gravitational wave we detect, every galaxy rotation curve we measure, carries echoes of quantum foam's whispers, reminding us that the universe's grand design might be written in the language of chaos. As we turn from spacetime's turbulent depths to gravity's role in shaping cosmic destiny, one thing becomes clear: the patterns we see in the heavens aren't just accidents of physics. They're signatures of a hidden order, a blueprint where even the fiercest chaos finds its place in the cosmos's silent symphony. The universe is locked in a silent tug of war, an epic struggle between the relentless pull of gravity and the mysterious push of dark energy. On one side, gravity, the force that sculpts galaxies and binds stars, works tirelessly to slow the universe's expansion, pulling everything toward a possible eventual collapse. On the other, dark energy, an enigmatic repulsive force, drives the cosmos apart at an accelerating rate, as if space itself is being stretched from within. The outcome of this battle isn't just academic. It determines whether the universe will end in fire, ice, or something far more dramatic. Consider the evidence we've gathered so far. In the late 1990s, astronomers studying distant supernova made a shocking discovery. These exploding stars were fainter than expected, meaning the universe wasn't just expanding, it was speeding up. This revelation earned researchers the Nobel Prize and turned cosmology on its head. Dark energy, previously a fringe idea, became the leading explanation. But here's the twist: we still don't know what dark energy is. Is it a property of empty space itself, as Einstein's cosmological constant suggested? Or is it something more exotic, a dynamic field that could change over time? The answer lies in the gravitational patterns imprinted on the cosmos, etched into the distribution of galaxies and the echoes of the Big Bang. Gravity's fingerprints are everywhere in this puzzle. Take galaxy clusters, the universe's largest gravitationally bound structures. By measuring how these clusters grow over time, how their gravity pulls in new galaxies and gas, scientists can weigh the competing influences of dark energy and gravity. Some observations suggest dark energy's strength might not be constant but increasing, which could lead to a big rip, a scenario where galaxies, stars, and even atoms are torn apart in a runaway expansion. Other data hints at a more subdued fate, a slow, cold expansion where galaxies drift apart until the cosmos becomes a vast, lifeless void. Yet there's a third possibility, one where gravity eventually wins. If dark energy weakens over time, the universe's expansion could reverse, collapsing back into a fiery, big crunch. This wouldn't be a simple rewinding of the cosmic clock. It would be a chaotic, violent process where galaxies collide, black holes merge, and spacetime itself crumples. Gravitational waves from such an event would be unlike anything we've detected, carrying the death cries of stars and the groans of collapsing space. The stakes couldn't be higher. The universe's fate isn't just about distant galaxies, it shapes the very conditions for life. If gravity and dark energy were even slightly different, stars might never have formed, planets might never have coalesced, and the delicate balance that allows chemistry and life to exist would vanish. This idea, known as the anthropic principle, suggests that the universe's gravitational fine-tuning isn't an accident. It might be a prerequisite for our existence, a hidden line in the cosmic blueprint that makes life possible. Now imagine a universe where gravity was stronger. Galaxies would collapse too quickly, leaving no time for stars to ignite or planets to cool. Or one where dark energy dominated earlier, tearing apart protogalactic clouds before they could birth stars. The fact that we're here to ponder these questions hints at an eerie truth. The laws of physics, and gravity in particular, seem calibrated to allow life to emerge. Whether this is coincidence, necessity, or something more profound remains one of cosmology's deepest mysteries. As we peer deeper into the cosmos, mapping its expansion with ever greater precision, we're not just forecasting the universe's end, we're uncovering the hidden rules that govern its entire existence. And with each new observation, each subtle gravitational clue, we move closer to answering the ultimate question: Is our universe's fate written in the stars, or is it still being decided in the silent war between gravity and dark energy? Gravitational fine-tuning is one of the universe's most baffling open secrets, a series of cosmic coincidences so precise they border on the miraculous. Take gravity's strength. If it were just slightly stronger, stars would burn too hot and fast, exhausting their fuel before life could emerge. A fraction weaker, and stellar cores wouldn't ignite at all, leaving the cosmos dark and lifeless. Even the force's long-range behavior is suspiciously perfect, strong enough to sculpt galaxies yet weak enough to allow delicate planetary orbits. It's as if the universe's dials were set with razor-sharp precision, all pointing toward a single improbable outcome, the possibility of life. This fine-tuning extends beyond gravity alone. The cosmological constant, which governs dark energy's repulsive force, is calibrated to 1 part in 10 to the 120th power, a number so absurdly precise it's like balancing a pencil on its tip for billions of years. Even the initial density fluctuations after the Big Bang, which gravity amplified into galaxies, were just right, too smooth, and matter would never clump, too uneven, and black holes would dominate. Together, these factors form what physicists call the Goldilocks principle, conditions that are not too hot, not too cold, but inexplicably perfect. So what explains this cosmic precision? One compelling answer is the multiverse theory, the idea that our universe is just one bubble in an infinite froth of realities, each with different physical constants. In most, gravity might be too strong or weak for complexity to arise. We find ourselves in a habitable one not by design, but by sheer probability. It's the only kind where observers like us could exist to ponder the question. It's a cosmic version of survivorship bias, like a lottery winner marveling at their luck while ignoring the millions of losing tickets. Yet the multiverse isn't the only possibility. Some theorists propose that gravity's fine-tuning hints at deeper laws we've yet to uncover, a theory of everything that inherently balances the constants. Others entertain even wilder ideas, that the universe is a simulation, its parameters deliberately set, or that gravity's apparent precision emerges from interactions with hidden dimensions. Each explanation carries profound implications, not just for physics but for our place in the cosmos. Are we the unlikely winners of a cosmic dice roll, or is the universe inherently biased toward life? Now, imagine bending these finely tuned laws to our will. Wormholes, hypothetical tunnels through spacetime, offer a tantalizing glimpse of what might be possible if gravity's rules could be rewritten. Predicted by Einstein's equations but never observed, these shortcuts could connect distant points in the universe like cosmic subway lines. Picture folding a sheet of paper so 2 dots touch. A wormhole would be the penstroke bridging them, turning a journey of billions of light years into a stroll across the room. The catch: wormholes demand conditions that border on fantasy, exotic matter with negative energy to prop them open, and gravitational forces so finely controlled they'd make the universe's existing fine-tuning look crude. Yet their theoretical existence hints at a startling idea, that gravity's patterns might not just shape the universe, but could one day let us reshape it. Whether through wormholes, warp drives, or technologies we can't yet fathom, the same force that sculpted galaxies might someday knit them together. And as we unravel gravity's secrets, we're not just decoding the universe's blueprint, we're glimpsing our potential to rewrite it. Wormholes aren't just science fiction, they're cosmic shortcuts theoretically woven into the fabric of spacetime itself. Picture folding a piece of paper so 2 distant dots touch, then poking a hole through the crease. That's the essence of a wormhole, a tunnel connecting far-flung regions of the universe, a gravitational loophole that could turn a journey of billions of light years into a stroll across the room. Einstein's equations of general relativity don't just allow for such structures, they predict their possibility. Yet for all their mathematical elegance, wormholes remain tantalizingly out of reach, hidden in the fine print of physics where theory and observation haven't yet met. What makes wormholes so fascinating isn't just their potential as interstellar highways, it's how they blur the line between gravity and quantum mechanics. Some models suggest that entangled particles, those spooky twins of quantum physics that mirror each other instantaneously across vast distances, might be linked by microscopic wormholes. It's as if the universe has built-in backdoors, threading spacetime with connections that defy classical logic. This idea, dubbed ER equals EPR after the papers that proposed it, hints at a profound unity. Gravity's warping of spacetime and quantum entanglement could be two sides of the same cosmic coin. But don't pack your bags for a wormhole voyage just yet. The challenges are as monumental as the possibilities. Stable wormholes would require exotic matter with negative energy, a substance that repels rather than attracts, counteracting gravity's crushing grip. While quantum physics allows for fleeting bursts of negative energy in phenomena like the Casimir effect, sustaining enough to prop open a traversable wormhole is another matter entirely. The energy demands are astronomical and the engineering pure speculation. Even if such matter existed, a single misstep could collapse the tunnel into a black hole or unleash catastrophic feedback loops, like a microphone screech echoing through spacetime itself. Yet the allure persists. Wormholes don't just promise shortcuts through space, they could bridge times, linking moments separated by eons. Some solutions to Einstein's equations suggest wormholes might function as time machines, with one mouth aging slower than the other due to relativistic effects. The paradoxes this introduces, like meeting your past self or rewriting history, aren't just plot holes for sci-fi writers. They're serious challenges that make physicists question whether the universe has built-in safeguards, like quantum mechanics, chronology protection conjecture, which might prevent such loops from forming. The deeper we dig into wormholes, the stranger the connections become. Holography, the radical idea that our three-dimensional universe might be a projection from a two-dimensional boundary, reimagines gravity itself as an emergent phenomenon, a shadow cast by quantum interactions at the edge of reality. In this framework, wormholes could be geometric representations of quantum entanglement, their tunnels mapping onto the invisible threads linking particles across the cosmos. It's a vision where spacetime isn't fundamental but stitched together from deeper, more primal relationships, like a tapestry woven from information rather than matter. This convergence of gravity and quantum theory isn't just academic, it's rewriting our understanding of reality's blueprints. If holography holds, then wormholes might not be anomalies but inevitable features of a universe where space and time are secondary to the quantum connections beneath them. The implications ripple outward. Black holes could encode their secrets on distant surfaces. Cosmic events might be linked in ways we're only beginning to glimpse, and the very fabric of existence could be far more malleable than Einstein ever dreamed. As we stand at this crossroads of theory and imagination, one thing is clear: wormholes are more than mathematical curiosities. They're portals to a deeper truth, that gravity's patterns might be the visible strokes of a far grander design, one where the universe's hidden threads wait to be pulled, revealing connections we've only just begun to trace. The holographic principle turns our understanding of reality inside out literally. Imagine the universe as a cosmic movie screen where everything we experience, stars, galaxies, even the force of gravity, is just a three-dimensional projection from information painted on a distant two-dimensional surface. This isn't science fiction. It's a serious theory born from the study of black holes, where the amount of information a black hole can hold doesn't scale with its volume but with its surface area. It's as if the universe has been playing a trick on us all along, hiding its true workings on a boundary we can't see. At the heart of this idea is gravity's strangest behavior. Unlike other forces, gravity doesn't seem to follow the rules of quantum mechanics, resisting unification with the other fundamental forces. But if gravity isn't a force in the traditional sense, if it emerges from information encoded on the universe's edges, then its stubborn refusal to fit quantum models starts to make sense. Think of it like a shadow puppet show. The movements of the puppets, our 3D reality, are dictated by unseen hands manipulating the flat surface behind them, the 2D boundary. Gravity, in this view, isn't pulling objects together. It's a side effect of how information on that boundary interacts and evolves. The implications are staggering. If the holographic principle holds, then the gravitational patterns we observe, the way galaxies cluster, the bending of light around massive objects, aren't just features of our universe but echoes of processes happening on a distant, invisible surface. This would mean dark matter's gravitational effects might not come from invisible particles, but from information we're not accounting for in our equations. Even black holes, those cosmic enigmas, could be reinterpreted as patches where the projection breaks down, revealing glimpses of the universe's underlying code. Yet the principle faces its share of challenges. For one, it predicts subtle deviations from Einstein's general relativity, tiny gravitational anomalies that should appear in extreme environments, like near the event horizons of rapidly spinning black holes or in the early universe's inflationary period. So far, these deviations haven't been conclusively observed, but new tools like next-generation gravitational wave detectors and precision measurements of the cosmic microwave background are hunting for these fingerprints. A single confirmed anomaly could upend centuries of physics, proving that gravity isn't fundamental but emergent, a holographic illusion. What's most mind-bending is how this idea connects to quantum entanglement. In the holographic framework, entangled particles, those spooky twins that mirror each other across vast distances, might be linked by microscopic wormholes threading the boundary. This suggests that entanglement and gravity are two sides of the same coin, a duality that could finally bridge quantum mechanics and general relativity. It's as if the universe has been whispering its secrets in a language we're only now learning to decipher. Whether the holographic principle is ultimately proven or not, it forces us to rethink the very nature of reality. If gravity is a projection, then the cosmos isn't just a collection of objects in space, it's a dynamic, interconnected system where every event, from the birth of a star to the collision of black holes, is a note in a symphony played on the universe's edge. And as we peel back these layers, we're not just solving equations, we're uncovering the hidden rules of a cosmic game where space, time, and gravity might just be the opening moves. Gravity is supposed to be the universe's most predictable force, governed by equations we've trusted for over a century. Yet scattered across the cosmos are glitches in the system, anomalies that defy explanation, like cosmic error messages blinking in the dark. Take the Pioneer anomaly. As NASA twin Pioneer probes drifted toward the edge of our solar system in the 1980s, they slowed ever so slightly more than Einstein's formulas predicted. This wasn't equipment failure or solar wind. It was as if some unseen hand tugged at the spacecraft, a gravitational hiccup no one could account for. Decades later, the mystery lingers, with proposed solutions ranging from heat radiation effects to the radical possibility that gravity behaves differently at the solar system's frozen edges. Then there's the dark flow phenomenon, entire galaxy clusters streaming in the same direction at baffling speeds, as though pulled by something beyond the observable universe. This isn't just peculiar, it's cosmically unsettling. Our best maps show the universe expanding uniformly in all directions, yet these clusters move like leaves caught in a hidden current. Some theorists suggest they're responding to gravitational tides from other universes in a vast multiverse, their invisible pull warping spacetime on scales we can't yet measure. Others propose flaws in our understanding of dark energy's distribution, or even undiscovered types of matter warping gravity itself. The Bullet Cluster offers another gravitational riddle. When two galaxy clusters collided, their visible gas clouds slowed and heated up, but their dark matter, detected through gravitational lensing, kept racing ahead like a phantom runner crossing a finish line we can't see. This confirmed dark matter's existence but deepened the mystery of why it refuses to interact with light or ordinary matter in any detectable way. Meanwhile, certain dwarf galaxies orbit the Milky Way in a suspiciously flat plane, a configuration standard dark matter models struggle to explain. It's as if gravity's rulebook changes when we're not looking, switching between invisible ink and bold print. These anomalies aren't just academic curiosities, they're stress fractures in our cosmic models, cracks where new physics might seep through. Modified gravity theories like tweak Einstein's equations to explain galactic rotations without dark matter, while string theory suggests extra dimensions could subtly alter gravity's strength over vast distances. Some experiments even hunt for chameleon particles, hypothetical entities that change mass based on their environment, potentially accounting for gravity's apparent mood swings. Enter artificial intelligence, the newest tool in this gravitational detective kit. Machine learning algorithms now sift through mountains of telescope data, spotting subtle patterns human eyes might miss. At the Laser Interferometer Gravitational Wave Observatory, AI helps distinguish genuine gravitational waves from instrumental noise, like picking out a whisper in a hurricane. Other programs map dark matter's distribution by analyzing how it bends light from millions of galaxies, reconstructing the invisible cosmic web strand by strand. The most ambitious projects train neural networks to simulate universes with alternate physics, testing whether tweaked gravity laws could birth the anomalies we observe. What makes AI indispensable isn't just its speed, it's its ability to connect dots across disciplines. By cross-referencing gravitational lensing maps with galaxy motions and cosmic microwave background data, these systems uncover relationships no single human team could trace. Already, they've flagged peculiar galactic collisions where gravity behaves oddly, hinting at environments where our theories might break down. As telescopes like Euclid and the Vera Rubin Observatory flood servers with petabytes of new observations, AI will be our guide through the data deluge, pointing to where the universe's hidden design might reveal its next clue. The beauty of these gravitational puzzles isn't just in their solutions, it's in how they remind us that the cosmos still holds cards close to its chest. Every anomaly, every deviation from expectation, is a potential doorway to discoveries that could reshape physics. Whether the answers lie in unseen dimensions, revised equations, or forces beyond our current imagination, one thing is certain: gravity still has stories left to tell, written in the silent tug between stars and the invisible arcs of spacetime itself. Artificial intelligence is revolutionizing our search for cosmic order, sifting through the universe's noise to uncover whispers of hidden design. When the Hubble Space Telescope beams down images of distant galaxies, it's not just astronomers scrutinizing the data. Machine learning algorithms pass millions of pixels in seconds, flagging subtle distortions that betray the presence of invisible mass. These AI systems don't just work faster than humans, They spot connections we'd never think to look for. In 2021, a neural network trained on simulated gravitational lenses discovered dozens of real ones in telescope data, warps in spacetime so faint they'd eluded detection for years. Each lens is a cosmic magnifying glass, bending light around unseen dark matter, and now AI is mapping this invisible scaffolding at unprecedented scales. But the real magic happens when these systems tackle problems too complex for traditional physics. Take black hole mergers. Supercomputers require weeks to simulate the gravitational waves produced by colliding black holes, solving Einstein's equations step by painstaking step. AI models trained on thousands of these simulations can predict wave patterns in milliseconds and with startling accuracy. Some have even spotted anomalies in real LIGO data, gravitational wave glitches that might hint at exotic physics, like boson stars or primordial black holes lurking in the cosmic background. It's as if we've given the universe a new language to speak, one where gravity's secrets emerge from patterns too intricate for human minds to untangle alone. The next frontier lies in the unseen torrent of neutrinos flooding the cosmos, ghostly particles so indifferent to matter they pass through entire planets like moonlight through glass. Yet even these phantoms feel gravity's pull. When a supernova explodes, its neutrino burst arrives at Earth slightly ahead of the light, delayed by the warped spacetime around the dying star. AI networks now track these subtle delays across detectors worldwide, reconstructing gravity's imprint on particles that barely interact with anything at all. The goal: to catch neutrinos bending around black holes or clustering along dark matter filaments, behaviors that could reveal how gravity operates at scales where quantum weirdness and cosmic forces collide. What makes this partnership between machine and cosmos so transformative isn't just speed, it's perspective. AI doesn't approach data with human biases or preconceptions. It might find gravitational lenses shaped like pretzels, black holes spinning backward, or neutrino streams aligned in geometries that defy textbook physics. Every anomaly is a potential clue, a crack in our understanding where new theories could shine through. As telescopes like the Vera Rubin Observatory unleash avalanches of data, these algorithms will be our guides, tracing gravity's hidden blueprint through the chaos, one unexpected pattern at a time. Neutrinos are the universe's ultimate ghosts, particles so elusive they can pass through light years of lead without a single collision. Yet these nearly weightless phantoms, born in the hearts of stars and the fury of supernova, might hold the key to unraveling gravity's deepest mysteries. Every second, trillions of neutrinos stream through your body unnoticed, a silent cosmic rain left over from the Big Bang and ongoing stellar explosions. Their indifference to matter makes them nearly impossible to detect, but their subtle dance with gravity could rewrite our understanding of physics. Take the Ice Cube Neutrino Observatory, a sprawling detector buried deep in Antarctic ice. When a rare neutrino does interact, it creates a faint blue flash, a signal so delicate it requires thousands of sensors to capture. But the real treasure lies in where these neutrinos come from. In 2017, IceCube traced a high-energy neutrino back to a blazar, a supermassive black hole spearing the cosmos with jets of radiation. The journey wasn't straightforward. This neutrino had traveled 4 billion light-years, threading through galaxies and dark matter filaments, its path ever so slightly bent by gravity along the way. By mapping these bends, scientists can weigh the invisible structures it passed through, like cosmic surveyors measuring the universe's hidden scaffolding. What's astonishing is how neutrinos defy expectations. According to general relativity, all objects regardless of mass should fall at the same rate in a gravitational field. Yet some theories suggest neutrinos, with their vanishingly small masses, might deviate in ways too subtle to notice with current tools. If they do, it could hint at extra dimensions or unknown forces tweaking gravity at quantum scales. Imagine dropping a feather and a bowling ball in a vacuum. They hit the ground simultaneously. But if the feather wobbles ever so slightly, it might reveal air currents you never knew were there. Neutrinos could be that feather, exposing hidden ripples in spacetime's fabric. The stakes get even higher when neutrinos meet black holes. As these particles skim a black hole's event horizon, their paths twist into spirals, encoding information about the hole's spin and mass in their final trajectory. Some models predict that neutrinos could even carry echoes of quantum gravity, effects tiny tremors in their behavior that betray the granularity of spacetime itself. It's like listening to a whisper reverberate through a canyon. The distortions tell you about the walls you can't see. Now, shift focus from the vastness of space to the cramped confines of extra dimensions. String theory proposes that our universe might have hidden spatial dimensions curled up smaller than an atom. Gravity, unlike other forces, could leak into these dimensions, explaining why it feels so weak compared to electromagnetism or the nuclear forces. Neutrinos offer a unique way to probe this idea. If extra dimensions exist, they might slightly alter how neutrinos oscillate, changing flavors between electron, muon, and tau types as they travel. Experiments like Dune and Hypercamioc are hunting for these anomalies, using colossal tanks of liquid to catch neutrinos in the act of transformation. The beauty of neutrinos lies in their duality. They're both cosmic messengers and quantum puzzles. Their near masslessness makes them ideal for testing gravity's limits, while their sheer abundance turns the entire universe into a laboratory. Every time one of these phantoms is caught in a detector, it's not just a particle being recorded, it's a ripple in the fabric of reality, a clue to forces and dimensions beyond our current grasp. And as we decode their secrets, we're not just studying neutrinos, we're reading the universe's hidden blueprints, written in the language of gravity itself. String theory paints a picture of reality far stranger than our everyday experience, a universe where space isn't just the three dimensions we know, but a tapestry woven with hidden folds and curls. Imagine a garden hose lying on the ground. From a distance, it looks like a simple line, but up close, you see its circular surface. In the same way, our universe might harbor extra spatial dimensions, coiled so tightly they're invisible to even the most powerful microscopes. These dimensions aren't just mathematical curiosities. They could solve one of physics' greatest puzzles: why gravity is so weak compared to the other fundamental forces. While electromagnetism can lift a paperclip against Earth's entire gravitational pull, gravity's feebleness might not be intrinsic. Instead, its influence could be leaking into these unseen dimensions, diluting its strength in our observable world like water seeping into hidden cracks. Gravitational waves might be our best tool for detecting these hidden realms. When black holes collide, they send ripples through spacetime that travel across the cosmos. But if extra dimensions exist, these waves could carry subtle fingerprints of their geometry. One telltale sign would be breathing modes, where gravitational waves exhibit rhythmic fluctuations as they stretch and compress higher dimensional space. It's like listening to a bell ring in a cathedral. The echoes don't just tell you about the bell, they reveal the shape of the entire building. Advanced detectors like LISA, a future space-based observatory, could catch these whispers, uncovering whether gravity's hidden dimensions are compact curls, warped membranes, or even vast, parallel universes brushing against our own. Yet the implications stretch beyond gravity alone. If extra dimensions exist, they might weave consciousness itself into the fabric of the cosmos. This isn't New Age speculation. It's a frontier explored by physicists like Sir Roger Penrose, who suggests quantum processes in the brain could interact with spacetime's fundamental structure. In this view, the brain isn't just a computer made of meat. It might be a quantum antenna, tuned to vibrations in dimensions we can't yet perceive. Near-death experiences, sudden bursts of creativity, even the hard problem of consciousness. These could be glimpses of a deeper, multidimensional reality where mind and cosmos intertwine. The idea resonates with ancient traditions that envisioned consciousness as a bridge between worlds. Hindu cosmology describes higher planes of existence, while Plato's cave allegory hints at realities beyond our sensory prison. Modern physics, armed with equations instead of myths, now asks whether these intuitions were metaphorical approximations of a truth we're only now quantifying. Could the brain's neural networks, with their fractal branching and quantum coherence, be echoes of the universe's hidden geometry? Experiments like quantum entanglement in photosynthesis or the orchestrated objective reduction theory probe these possibilities, searching for links between subjective experience and objective physics. What's certain is this: the universe's design might be far richer than we've dared to imagine. From gravity's whisper in hidden dimensions to the mind's potential resonance with cosmic structure, we're uncovering a blueprint where matter, energy, and consciousness aren't separate phenomena but interconnected notes in a multidimensional symphony. And with each discovery, we're not just mapping the cosmos, we're rediscovering our place within it. Consciousness might be the most perplexing frontier in science, an intimate mystery each of us experiences, yet one that resists explanation. While mainstream physics treats the mind as a byproduct of brain activity, a provocative fringe idea suggests something far stranger: that consciousness could interact directly with spacetime or gravity, shaping reality in ways we're only beginning to imagine. This isn't mysticism repackaged. It's a hypothesis grounded in the peculiarities of quantum mechanics, where observation appears to alter the behavior of particles. At the heart of this debate lies a radical question: could the universe's gravitational patterns and the emergence of consciousness share a hidden connection? Consider the observer effect in quantum experiments. When scientists measure a particle's position or spin, its wave function collapses from a haze of probabilities into a definite state. The act of observation, conscious or otherwise, seems to play a role in this process. Some theorists, like Nobel laureate Roger Penrose, propose that this collapse isn't random but guided by gravitational instabilities at the quantum scale. In this view, consciousness isn't a passive witness but an active participant, its very presence tipping the scales in spacetime's delicate balance. Penrose and anesthesiologist Stuart Hameroff take it further with their orchestrated objective reduction theory, suggesting microtubules in brain neurons might harness quantum gravity to produce conscious experience. It's as if the mind isn't just riding the universe's waves, it's helping to shape them. The implications ripple outward. If consciousness interacts with gravity, could collective human thought leave faint imprints on spacetime itself? Studies like the Global Consciousness Project claim to detect subtle correlations between major world events and random number generators, as if mass attention briefly warps probability. Skeptics dismiss these findings as statistical noise, but the underlying idea echoes an ancient intuition: that mind and cosmos are entwined in ways beyond material cause and effect. Eastern philosophies have long described consciousness as fundamental, with Hindu texts envisioning Brahman as a cosmic mind and Buddhist teachings asserting that perception constructs reality. Modern physics, in its most speculative reaches, now dances around similar notions, probing whether the universe might be more like a vast, self-aware network than a cold, mechanical clock. Yet for all its intrigue, this idea remains fiercely controversial. Critics argue that conflating consciousness with quantum processes ignores the brain's obvious biological machinery, billions of neurons firing in complex but classical ways. They point out that no experiment has conclusively shown human thought altering gravitational fields or quantum states beyond known physical limits. The burden of proof rests heavily on those claiming such extraordinary links. But even as the debate rages, it raises profound philosophical questions. If gravity's patterns sculpt galaxies and consciousness emerges from those same physical laws, are we merely bystanders in the cosmos or participants in its unfolding design? Future missions might edge us closer to answers. The Laser Interferometer Space Antenna LISA, set to launch in the 2030s, will hunt for gravitational waves with unprecedented precision. While its primary goal is studying black hole mergers, subtle anomalies in wave patterns could reveal unexpected interactions between gravity and quantum systems. Closer to home, experiments with supercooled quantum sensors aim to detect whether conscious observation alters gravitational measurements at microscopic scales. These aren't searches for psychic phenomena, but rigorous tests of whether mind and spacetime share deeper ties than our current physics allows. Whether these explorations confirm or debunk the consciousness-gravity link, they underscore a timeless truth: the universe is far stranger than we've dared to dream. From the quantum foam beneath our feet to the gravitational webs connecting galaxies, reality hums with patterns we're only beginning to trace. And as we peer deeper, we're left to wonder, are we decoding the cosmos, or is the cosmos, in some ineffable way, decoding us? Future missions are poised to peel back the universe's deepest layers, turning speculative theories into concrete data. The Laser Interferometer Space Antenna, or LISA, isn't just another space observatory, it's a gravitational wave hunter with a sensitivity so refined it could detect the ripples from supermassive black holes merging at the dawn of time. Unlike ground-based detectors like LIGO, which catch high-frequency waves from stellar mass collisions, LISA trio of spacecraft, floating 2.5 million kilometers apart, will tune into the universe's low-frequency hum. Imagine listening to a symphony where previous instruments only caught the cymbals and trumpets, while LISA reveals the cellos and double basses, the deeper, richer notes that carry the cosmos's oldest stories. These waves could expose the gravitational fingerprints of cosmic strings, hypothetical defects in space-time left over from the Big Bang, or even reveal hidden dimensions warping the fabric of reality. Meanwhile, the Nancy Grace Roman Space Telescope will tackle one of gravity's greatest enigmas, dark matter's invisible architecture. By mapping how light bends around unseen mass across billions of galaxies, Roman will create the most detailed 3D chart of the cosmic web ever assembled. But it's not just about filling in the blanks. This telescope could settle the debate between dark matter and modified gravity theories once and for all. If dark matter particles exist, Roman's lensing surveys might catch their subtle clumping patterns around galaxies. If instead gravity operates by unseen rules, the telescope's precision measurements could reveal telltale deviations from Einstein's predictions at galactic scales. Either outcome would rewrite textbooks, but the real prize lies in the anomalies, the places where the data refuses to fit our models, hinting at physics beyond our wildest conjectures. Then there's the Einstein telescope, a next-generation underground observatory designed to catch gravitational waves with 10 times LIGO precision. Buried deep beneath Europe to shield it from seismic noise, this instrument could detect the faint echoes of primordial black holes, hypothetical relics from the universe's first second, or even waves from cosmic inflation itself. Picture capturing vibrations from an event so ancient It predates stars, galaxies, and light itself. These missions aren't just incremental upgrades, they're leaps into the unknown, armed with tools that could finally decode gravity's role in the universe's birth, evolution, and ultimate fate. But why does this matter beyond scientific curiosity? Because gravity's secrets are woven into everything, from the stability of planets to the expansion of space itself. Unraveling them could redefine our place in the cosmos. If Lisa finds evidence of extra dimensions, it might open doors to technologies that sound like science fiction today. If Roman confirms dark matter's nature, we could harness its properties in ways we can't yet imagine. And if these missions expose flaws in Einstein's relativity, the implications would ripple through everything from GPS satellites to our understanding of time. This isn't just about mapping the universe, it's about discovering the hidden rules that have shaped existence since the first moment of time, and learning how to read the blueprint we've been handed. For thousands of years, humanity has gazed upward, searching the stars for meaning and order. Ancient Babylonian priests tracked planetary motions with astonishing precision, believing celestial patterns held divine messages. Polynesian navigators memorized the gravitational pull of distant islands on ocean currents, charting courses across trackless seas. Even our earliest myths wove the heavens into stories of creation, sensing, though not yet understanding that the cosmos operated by rules waiting to be uncovered. Today, armed with telescopes and supercomputers rather than star charts and oral traditions, we continue this timeless quest, but the questions have evolved from "what do the gods whisper?" to "what laws does the universe obey?" A shift from mysticism to mathematics, yet driven by the same fundamental urge to decode existence. This journey has led us to an astonishing realization. Gravity isn't just a force, it's the architect of reality. From the quantum foam flickering beneath our feet to the cosmic web spanning billions of light years, gravity's patterns form a hidden blueprint. Consider how this shapes our modern worldview. Where ancient cultures saw gods shaping the heavens, we now map dark matter filaments. Where astrologers read fate in planetary alignments, astrophysicists measure gravitational waves from colliding black holes. The language has changed, but the awe remains, a testament to humanity's unbroken drive to find order in the chaos. What makes our current era unique isn't just the sophistication of our tools, but the scale of our ambition. Projects like LISA aim to capture gravitational echoes from the universe's first moments, while quantum gravity experiments probe spacetime's fabric at scales 1 trillion times smaller than an atom. We're no longer passive observers of cosmic design. We've become active participants in its revelation. This shift mirrors the Copernican revolution in reverse, where once we learned Earth wasn't the center of the universe, now we're discovering how deeply we're woven into its structure. The iron in our blood was forged in dying stars, our planet's orbit shaped by gravitational dances with Jupiter and the Sun, even our perception of time warped by Earth's mass. We're not just studying the cosmos, we're made of it, shaped by the same forces we're striving to understand. Yet with each discovery comes deeper mystery. Dark energy accelerates the universe's expansion, but we don't know why. Quantum mechanics and general relativity describe reality with uncanny accuracy, yet refuse to unite. Somewhere between these puzzles may lie the next great leap, a theory that doesn't just explain gravity, but reveals its connection to consciousness, time, and the very nature of existence. The ancient stargazers would recognize this pursuit, though its form has transformed beyond their wildest dreams. Their constellations told stories of heroes and monsters. Ours reveal black holes, neutron stars, and gravitational lenses. But both traditions share a common thread, the conviction that the heavens speak, if only we learn to listen. as we stand on the threshold of new revelations, from wormholes to extra dimensions, from emergent gravity to cosmic holograms. We're continuing humanity's oldest and most profound adventure. Not just to map the stars, but to read the universe's hidden language. Not just to measure gravity's pull, but to understand how it sings the cosmos into being. Every equation we solve, every anomaly we uncover, brings us closer to answering questions that have haunted us since the first campfires flickered under starry skies. Why is there something rather than nothing? And what role do we, conscious, questioning stardust, play in this grand design? The journey isn't ending. It's just begun. The universe has always whispered its secrets in the language of gravity, a code written in the spirals of colliding black holes, the ghostly pull of dark matter, and the delicate warp of space-time around cosmic voids. What we're witnessing now isn't just a series of isolated discoveries, but the gradual unveiling of a grand design, one where chaos gives way to hidden order. Every ripple in spacetime detected by LIGO, every filament of the cosmic web mapped by Euclid, adds another stroke to this evolving masterpiece, and the most astonishing part. We're not just observers of this revelation, we're active participants, our curiosity and tools chiseling away at mysteries that have waited billions of years to be solved. Take black hole mergers as an example. These cataclysmic events aren't just cosmic spectacles, they're precision laboratories for testing gravity's limits. When two black holes collide, their gravitational waves carry imprints of their masses, spins, and even the geometry of the spacetime they warped. It's as if each merger leaves behind a fingerprint, unique and packed with information. Some of these fingerprints have already defied expectations, black holes merging at impossible angles, or with masses that shouldn't exist. These anomalies aren't glitches, they're clues, hinting at physics beyond Einstein's equations, perhaps even pointing toward extra dimensions or exotic forms of matter. Then there's dark matter, the universe's silent scaffolding. We can't see it, touch it, or directly detect it, yet its gravitational influence is everywhere. The way galaxies rotate too fast, the way light bends around seemingly empty space, these aren't cosmic errors but evidence of an invisible hand shaping reality. Some theories suggest dark matter could be particles unlike anything in our standard model, while others propose it's a sign that gravity itself operates differently on galactic scales. The truth might lie somewhere in between or in a direction we haven't yet imagined. What's clear is that solving this riddle won't just fill a gap in our textbooks, it could rewrite them entirely. And let's not forget the cosmic web, that vast network of filaments and voids stretching across the observable universe. These structures aren't random, they're the aftermath of quantum fluctuations amplified by gravity over eons, a delicate balance between attraction and expansion. Simulations show that without dark matter's gravitational glue, the universe would look nothing like it does today. Yet even our most advanced models can't fully explain why some filaments are so vast or why galaxies align in ways that defy prediction. These aren't just academic puzzles, they're windows into the universe's operating system, its hidden algorithms. What ties all these threads together is the growing realization that gravity isn't just a force, it's a narrative. It tells the story of how the universe grew from a seething quantum foam into the intricate tapestry we see today. And like any good story, it's full of twists. The discovery that the universe's expansion is accelerating, driven by dark energy, was a plot twist no one saw coming. The possibility that gravity might emerge from deeper, quantum processes like space-time itself being woven from entangled particles adds layers of intrigue. Even the anomalies, the things that don't fit, are part of the narrative, reminding us that the cosmos still has surprises up its sleeve. This is why the study of gravity feels so profoundly human. It's not just about equations or observations, it's about our place in the grand scheme. Every time we detect a gravitational wave or map a new piece of the cosmic web, we're not just collecting data, we're learning to read the universe's blueprint. And in doing so, we're answering questions as old as civilization. Where did we come from? What else is out there? Are the laws of nature fixed, or could they change over time or across space? The journey is far from over. With next-generation telescopes, gravitational wave detectors, and quantum experiments, we're on the verge of probing even deeper into the hearts of black holes, the nature of dark energy, and perhaps even the origins of spacetime itself. Each step forward will bring new mysteries, but that's the beauty of exploration. The universe doesn't give up its secrets easily, and that's what makes the pursuit so thrilling. So what do you think? Are we close to uncovering gravity's ultimate secrets, or is the cosmos still hiding its deepest truths? Drop your thoughts in the comments below, and if you've enjoyed this journey through the hidden blueprints of reality, don't forget to subscribe. The universe has so much more to reveal, and we're just getting